When a motor must be replaced, the replacement motor must be able to do the job. In all probability, it will be specified by a plant engineer, but he may only indicate a general motor type and horsepower rather than a particular make and model. It may be up to you to make sure that the actual motor you have will work. It must have the right output characteristics to drive the load. It also must be able to operate on the electrical power supply available. It should be at least as rugged in all respects as the replaced motor and have the right type of construction so that it can do the job without burning out. And mechanically it must fit and be suitable for the environment it will have to work in. To know whether you've got the right motor for the job, you need to be familiar with the specifications that you will find on its nameplate. The model number is usually a coded general description of the motor. It is a good idea to look up the code in the manufacturer's catalog. There may be information in the model number that does not appear otherwise on the nameplate. Stock or catalog numbers identify particular motors. If you can match a new motor with an old one by stock or catalog number, it should be identical in all respects. The first of the output specifications is horsepower. A replacement motor must produce the right horsepower. In an emergency, a motor with higher horsepower might be substituted, but it would operate at part load and therefore less efficiently. The rated speed of a replacement motor must be the same as that of the old motor in all cases. The speed listed is usually nominal full load speed. That is, this motor runs at about 3,450 RPM when producing 1 horsepower. If it is overloaded, it will slow down below this rated speed. Under less than full load, it will turn somewhat faster. But since it is a 2-pole AC motor, it will never run faster than its synchronous speed of 3,600 RPM when powered by 60 Hertz AC. As we have seen in the DC and AC motors programs, other types of motors have different output horsepower and speed characteristics. The service factor of a motor is also a basic output specification. SF1 means that this motor has a service factor of 1. Some motors have a service factor of 1.15, 1.25, or even 1.35. A motor with a service factor of 1.25 can actually produce 1.25 times its rated horsepower without damage, though its efficiency and power factor will be lower than at rated power. It will stand up better than a motor with a service factor of 1 if it must operate under overload conditions. Most motors are designed for continuous output at rated power, though some have a duty rating like 20 or 30 minutes in 1 hour. They need the off time to cool down. Do not use a motor rated for intermittent duty where it will run continuously at full load. The electrical input specifications include supply voltage. Any replacement motor must be suitable for the voltage available. This is a dual voltage motor that can be connected to operate on either 115 volts or 230 volts. These are nominal voltages which take into account typical line losses from 120 and 240 volt supplies. The actual voltage at the motor should be within 10% of the nameplate voltage. A motor rated for 230 or 220 volts may also be approved for operation from a 208 volt supply. If it is not, do not connect it to a 208 volt supply, even though 208 volts is just within the 10% limit. Actual voltage at the motor is likely to drop below 208 at least part of the time. Use a motor with a nominal voltage rating of 200 volts if your supply is 208 volts. PH1 means that this motor is designed for single-phase AC. Chances are most of the larger motors in your plant will be powered by 3-phase AC. A single-phase motor can be connected between two wires of a three-phase system if the voltage is right. But without special converters, there is no way to connect a three-phase motor to single-phase power. This motor is rated for 60 Hertz AC. Some 60 Hertz motors should not be operated on 50 Hertz AC and vice versa. Others can be, but remember that speed, current draw, and available horsepower will be different. The A on this nameplate stands for full load amperes. This is the current the motor will draw from each power line when producing its rated output power. The higher current applies when the motor is connected to the lower of the two voltages listed. If a replacement motor draws less current than the old one, it may be one of the new high-efficiency models. The nameplate label will probably indicate this somewhere, or it may be one of the facts that is coded into the model number. The full load amperage determines the overload protection required. If the replacement motor has a lower FLA rating, you will need to set the overload breakers to trip at lower current to protect the motor from burnout. If you are replacing one motor with another that draws more current, you must set the overload breakers for higher trip current. You may also need to install larger motor starting equipment, circuit conductors, and fuses or circuit breakers with a higher current rating. This particular nameplate does not specifically list an item that is sometimes very important: the locked rotor amperage, or LRA, the current that a motor will draw under startup and stall conditions. The LRA is likely to be 2.5 to 10 times as much as full load current. Circuit breakers or fuses must be able to handle that current. The nameplate does, however, list a code letter H. On the code chart in your study guide, you will find that a code H motor will draw from 6.3 to 7.1 kilovolt amperes per horsepower at stall or startup. To calculate the LRA, multiply the code letter range by the horsepower and divide by the supplied voltage in kilovolts. Suppose the motor is connected to 115 volts, which is 0.115 kilovolts. Since this is a 1 horsepower motor, the LRA is between 6.3 and 7.1 times 1 divided by 0.115. In other words, the LRA will be between 55 and 62 amperes, almost 5 times the full load amperes for this motor, 12.5 amperes. A replacement motor with a code letter higher in the alphabet than the original may blow fuses or trip breakers, particularly if it must start a high inertia load which comes up to speed slowly. Now, even if a motor is suitable for the electrical power available and is capable of producing the right horsepower and speed, it will not last long if it is not made to take the operating conditions. Operating temperature is particularly important. The ambient 40 item means that this motor should not be operated in any environment hotter than 40 degrees Celsius or 104 degrees Fahrenheit. A replacement motor should not have a lower ambient temperature rating than the old motor. Any operating motor is much hotter inside than the ambient temperature around it. The wire insulation must be able to stand the heat. Most nameplates now include a specification on the insulation class of the motor. This Class B motor can operate continuously at an internal temperature as high as 130 degrees Celsius or 266 degrees Fahrenheit without damage to the insulation. You can replace one motor with another of a higher insulation class. In other words, you can use a Class F motor in place of a motor with Class B insulation, but not the other way around. In older motors particularly, you may see a temperature rise rating instead of an ambient temperature and insulation rating. Again, do not replace one motor with another that has a lower temperature rise specification. This nameplate tells you that the motor has built-in thermal protection. There is a thermostat or high temperature limit switch that will open to shut the motor off if it gets too hot. The M stands for manual reset, which means that once the thermostat opens, it must be reset manually before the motor will run again. You may find a motor with a thermal overload that resets automatically. This can be dangerous in some situations, since the motor may restart without warning once it has cooled down. Do not replace a manual reset motor with an automatic reset motor. Housing open is this manufacturer's way of specifying the motor enclosure. This is an open motor, meaning that it is open to the air. An internal fan on the shaft pulls air in one end and pushes it out the other. This kind of motor should be used only where the air is clean and dry. If a motor is specified as open drip proof, vertical rain will not enter. Splashing liquid and rain slanted at 15 degrees or more from the vertical can enter, however, and cause problems. Open splash-proof motors offer more protection against splashing liquids. Do not replace a splash-proof motor with a drip-proof or general-purpose open motor unless it is shielded some other way. In dirty or wet environments, a totally enclosed model should be used. There are several types. This is a totally enclosed, fan-cooled motor. Instead of pulling air through the motor, the fan blows air over the outside of the motor housing. Without the fan, a totally enclosed motor is non-ventilated and relies on air convection to carry heat away from the housing. Totally enclosed motor housings often have ribs or fins on the outside to improve heat transfer. Totally enclosed air-over motors are intended to be mounted in an airstream for cooling. Fan and blower motors are often of this type. Explosion-proof motors are used in hazardous atmospheres. They are totally enclosed motors with an especially rugged housing designed to withstand an internal explosion of a particular vapor or gas without rupturing or touching off a general explosion in the atmosphere. An explosion-proof motor can be used anywhere. A nameplate will probably indicate what type of bearings the motor has, and this can be very important. Different types of bearings require different maintenance and allow different kinds of loads to be placed on the motor shaft. This motor has ball bearings. They are used where higher load capacity is required or where frequent relubrication is impractical. Sleeve bearings usually require routine oiling or greasing. The bearings on some motors are not intended for anything but a direct shaft coupling. Belt drives place considerable side loads on a motor's bearings. Larger motors are sometimes equipped with heavy-duty roller bearings rather than ball or sleeve bearings when they will be used in belt drive applications. Be sure the replacement motor has the right bearings for the application. The bearings in some motors allow mounting in any position. Others, however, must be mounted horizontally because the bearings will not take the vertical weight of the rotor. If there is any question, look up the specifications in the catalog. Finally, unless you are prepared to use adapters, the replacement motor had better fit exactly and have the right housing for the application. NEMA, the National Electrical Manufacturers Association, has standardized the shaft and mounting dimensions of many motors and established frame numbers to assure mounting compatibility between motors built by different manufacturers. This motor has a NEMA 56 frame. All motors with a 56 frame have a shaft 3.5 inches above the base and 4 mounting holes located as shown with respect to the shaft. The shaft itself is 5/8 of an inch in diameter and has a length and keyway dimensioned as shown. The dimensions of the motor otherwise, its length and diameter, are not specified. Many small motors of all kinds, single-phase, three-phase, and DC, are 56 frames. Most of them are 1 horsepower or under. Bigger motors have higher NEMA frame numbers. The letters following the basic frame size provide further information. T refers to the new NEMA standard adopted in 1964. The older standard has a U after the frame number. C means that the motor is suitable for mounting directly to a component by bolting to its face. It may or may not have a foot mounting bracket as well. C-face motors are very common in many frame sizes. Other special shafts, mounting flanges, or dimensions are indicated by other letters. Z means the shaft is non-standard in some way. In this case, it means a double-ended shaft. Your study guide contains a list explaining what other letters mean. All right, a nameplate can give you a lot of information about a motor, but it often leaves out something very fundamental. You know that this is a single-phase AC motor. But what kind of single-phase AC motor is it? Is it a shaded pole, inductive split phase, repulsion induction, capacitor start, capacitor run, universal, or synchronous motor? The operating characteristics of these motor types are quite different. The single capacitor on top of this motor pretty surely identifies it as a common capacitor start induction motor. You should know your motors and never replace one type with another. Like single-phase motors, three-phase AC motors can be several different types. The nameplate will clearly identify less common types like wound rotor motors. Standard three-phase induction motors are supplied in 4 NEMA designs: A, B, C, and D, with different torque and current curves. DC motors also are available in different types. A shunt wound motor will have radically different operating characteristics from a series, compound, or permanent magnet motor. Do not replace one type with another. Often, DC drive motors are matched to their controllers and must be replaced with the exact same motor from the same manufacturer to work properly. Now, once you are sure your replacement motor will do the job, you need to install it correctly. Be sure the power circuit is locked out before touching any wires. Connecting the power lines to a motor properly is critical. Proper grounding, either through a grounding wire or the conduit, is very important for safety. Usually there is a diagram on the nameplate label or terminal board that specifies connections for different voltages, speeds, and directions of rotation. Be sure to insulate the ends of any unused leads. They will probably have voltage on them when the motor is running and must not short against the motor frame or each other. Double check your connections carefully and make sure the motor runs the right direction before connecting it to a load that would be harmed by reverse rotation. Go through the proper alignment procedure to prevent vibration and excessive loads on the motor bearings. Be sure the load puts no end thrust on the motor shaft and that the rotor will operate in the midpoint of its end play. Motors must be bolted down to something solid. Both bearing and insulation failure are quicker in motors which vibrate or shake. Use full-size bolts and torque them properly. Drive belts should be properly aligned. Keep pulleys and sheaves as close to the motor as possible without interfering with shaft end play. If necessary, reset the overload breakers for the replacement motor, and then record the line current and voltage to the motor both during startup and after it is running under normal load. Let the motor operate long enough to be sure breakers or overloads will not trip and that it is not overheating. If you have installed the right motor for the job and done your job correctly, chances are good that the new motor will last a long time. So be sure you know what the application requires and that the motor you are installing matches it.